substitution. So the lesson is on integration by substitution, and it's basically rewriting the chain rule for derivatives in terms of an integration rule. So if we have a function capital F of g of x, it's a composite function, and we differentiate with respect to x by the chain rule. This is f prime, capital F prime evaluated at g of x times g prime of x, which means that the antiderivative of f prime of g of x, g prime of x dx is f of g of x. And if f of x is the antiderivative of a function little f of x, then, in other words, capital F prime of x equals little f of x. Then another way of writing this is that the integral of little f of g of x times g prime of x dx is capital F of g of x plus there's always an additive constant where capital F is the integral of little f. So this is a somewhat complicated looking formula, but when you work some examples and keep working examples, sooner or later it becomes pretty clear what's going on and what you can do. So for example, we have to solve the problem of integrating x squared plus 1 squared times 2x dx. And what you do is you have to observe that the derivative with respect to x of x squared plus 1 is 2x. So if you let g of x equals x squared plus 1, g prime of x is 2x. So what this is the integral of g of x squared, g prime of x dx. And if we let f of u be equal to u squared, what this is so the integral of x squared plus 1 squared times 2x dx is f of x squared plus 1 times 2x dx. If we let x squared plus 1 be gx, this is the integral of f of g of x, and 2x is g prime of x dx. And capital F of u is the integral of u squared du, which is a third u cubed plus a constant. So this is equal to f of capital F of g of x, which is 1/3 g of x cubed plus a constant. That's 1/3 x squared plus 1 cubed plus a constant. So the integral of x squared plus 1 squared times 2x dx is 1/3 x squared plus 1 cubed. That's what we just sort of worked out. And if we check, the derivative of 1/3 x plus 1 cubed is 1/3 times x squared plus 1, which is 1/3, 3 times x squared plus 1 squared times the derivative of x squared plus 1, which is 2x. These cancel, and you get exactly this. So learning how to integrate functions by hand is an art form. It's not like differentiation where there's certain set rules. Here you have to use your imagination a little bit. So suppose we have the integral of 5e to the 5x dx. If I think of g of x as being equal to 5x, so g prime of x is 5, this is the integral of e to the g of x is 5x, times 5, g prime of x du. And if I think of f of u as being e to the u, this is of the form f of g of x, g prime of x dx. The integral of f of u is the integral of e to the u, which is e to the u. So this is my function capital F of u. So this is capital F of g of x, which is e to the g of x, which is e to the 5x plus a constant. Are there any questions about this? This is a skill you have to learn, and it is always on the final exam if that's a concern to you. So you have x times x squared plus 1 squared. So this is almost like the problem we had before, dx, except we need a 2x here instead of an x. But you can always write 1 as a half times 2. This is 1/2 the integral of 2x. Half times 2 is just 1, so I haven't done anything. X squared plus 1 squared dx. And this integral I already did. This is 1/2, 1/3 x squared plus 1 cubed. So we get 1/6 x squared plus 1 cubed, and there's always an additive constant. Okay. So you should have done some of the homework problems, and let me just do 1 or 2 first, and then I'll continue with some of the other parts of this exercise, of this lesson. For example, in the homework in this section, number 13 is integrate the square root of 25 minus x squared times minus 2x dx. Now, it's given in this sort of funny form to make it easy to do. Because if you look at this, you should see that if you let g of x be equal to 25 minus x squared, g prime of x is minus 2x. So this is the integral of the square root of g of x, g prime of x dx. And if we let f of u be the square root of u, this is the integral of f of g of x, g prime of x dx. And this is going to be capital F of g of x plus a constant, where capital F of u is the antiderivative of f of u. F of u is u to the 1/2. And the integral of u to the 1/2 is 2/3 u to the 3/2. So what we get is this is 2/3 g of x, 25 minus x squared, to the 3/2. And plus a constant, of course. Then you check, you integrate, you differentiate this, and you get exactly what's inside the integral sign. Let's do number 27 in the homework. This is the integral of x over square root of 1 minus x squared dx. And again, you should notice that if you were to let g of x be equal to 1 minus x squared, g prime of x is minus 2x. Of course, you have a problem. You don't have minus 2x, you just have x. This would be better if this were minus 2x over the square root of 1 minus x squared. But the only way you can multiply x by minus 2 is if you also divide by minus 2. Because then it's just 1. So this is minus 1/2, taking this outside, the integral of minus 2x over the square root of 1 minus x squared dx, which is minus 1/2, the integral of, let's see, 1 minus x squared, 1 over the square root of something is that something to the minus 1/2 power times minus 2x dx. And now you see this is exactly of the form minus 1/2, the integral of g of x, that's 1 minus x squared to the minus 1/2, g prime of x dx. And if we integrate u to the minus 1/2, we get 2 times u to the 1/2, or 2 times the square root of u. So this is minus 1/2 times 2 times the square root of g of x, 1 minus x squared. Right? And the 2's cancel. So it's just minus the square root of 1 minus x squared. Any questions about this? Again, you should check. If you take minus the square root of 1 minus x squared and you differentiate it, you get minus, this is 1 minus x squared to the 1/2. So you get 1/2, 1 minus x squared to the minus 1/2 times the derivative of 1 minus x squared, which is minus 2x. And the minuses cancel and the 2's cancel, and you get exactly what you're supposed to get. So this is definitely the right answer. Now, integration in general is very hard to do. It's a skill. It's not a algorithm. And you have to be very clever sometimes about solving these problems. Suppose I have sine cubed of 3x times the cosine of 3x dx. We want to find an antiderivative. So it's helpful, for example, to remember that the derivative of the sine is the cosine. So this is like the integral of sine of 3x cubed cosine of 3x dx. Now, if we let g of x be the sine of 3x, g prime of x is 1/3, sorry, the derivative is of the sine of 3x is 3 times the cosine of 3x. So if I multiply and divide by 3, 1/3 sine of 3x cubed times 3 cosine 3x because 1/3 times 3 is just 1, so that's perfectly okay. This is 1/3 the integral of g of x cubed g prime of x dx. So this is 1/3 f of g of x times g prime of x dx, if f of u is just u cubed. So f of g of x is g of x cubed, sine 3x cubed. And the integral of u cubed is 1/4 u to the 4th. So we get 1/3, and then this integral is 1/4 g of x to the 4th plus a constant. 3 times 4 is 12. Sine 3x to the 4th plus a constant. And you can check, if you differentiate this, you get exactly what you're supposed to get. Any questions about this? Now, what's a little bit more subtle often is to compute a definite integral when you have to change variables or make a substitution. So if we have the integral from a to b of f of g of x, g prime of x dx. So this is now the definite integral from a to b. So if we let capital F of u be the antiderivative of little f du, and the integral of f of g of x, g prime of x dx, this is the antiderivative. This is capital F of g of x. So when we integrate, when we use the fundamental theorem of calculus, this integral is f of g of b minus f of g of a. It's just the antiderivative, that's this function, evaluated from a to b. This is exactly the integral from g of a to g of b of f of u du. So this is the change of variables formula for a definite integral. And the only way to understand this is to just look very carefully at the examples in the book and work a lot of problems by yourself. So let's look at some examples. Suppose we're integrating x times x squared plus 1 cubed dx from 0 to 1. So you might want to write this as 1/2 the integral from 0 to 1 of 2x times x squared plus 1 cubed dx. I've just multiplied by 1. 1/2 times 2 is 1. But now I have 2x, which is the derivative of x squared plus 1. So if I were to let g of x equal to x squared plus 1, and f of u is u cubed, this is 1/2 the integral from 0 to 1 of f of g of x, g prime of x dx. It's exactly in this form, where now a is 0 and b is 1. So this is 1/2 the integral from g of 0 to g of 1 of u cubed du. G of 0 is 1 and g of 1 is 2. This is 1/2 the integral from 1 to 2 of u cubed du. That's 1/2. The integral of u cubed is 1/4 u to the 4th, evaluated from 1 to 2. 1/2 times a 4th is an 1/8. 2 to the 4th is 16. 2 to the 4th is 16. 1 to the 4th is 1. So we get 15/8. So another way to look at this problem is we have the integral from 0 to 1 x times x squared plus 1 cubed dx. And we're going to make a substitution. We're going to let u equal x squared plus 1. So du is 2x dx, du dx is 2x. So this is 1/2 the integral from 0 to 1, x squared plus 1 u cubed, 2x dx is du. And we get right away, and when x is 0, u is 1, and when x is 1, u is 2. So we get again 1/2, 1/4 u to the 4th from 1 to 2, which is what we just evaluated. Here's another example. The integral from 1 to 5 of x over the square root of 2x minus 1 dx. So suppose we let u equal 2x minus 1. So du again is 2 dx. Du dx is 2. If I make this 2 and multiply by a half, this is still unchanged. So what I have is 1/2 the integral of 1 over the square root of u, that's u to the minus 1/2, 2x dx. Oops, sorry. What I wrote is correct, but it's not the best way to solve this problem. So let me do it differently. This is part of the rule that you have to be clever and lucky to figure out quickly what to do with these problems. Suppose I have the integral from 1 to 5 of x over square root of 2x minus 1 dx. I thought I would let u equal 2x minus 1, but then du dx is 2. And I don't have a 2 here, I have an x here. So I'm going to try something different. Suppose we let u be the denominator, the square root of 2x minus 1. So u squared is 2x minus 1. If I solve for x, 2x is u squared plus 1. So x is u squared plus 1 over 2. And dx du, I differentiate this with respect to u, I just get u, right? Because the derivative of u squared is 2u over 2 is just u. Derivative of 1 is 0. So dx is u du. So when I make my substitutions, I'm going to have an integral. This is 1 over u. And x is u squared plus 1 over 2. And dx is u du. And when x is 1, u is 1. And when x is 5, this is 10. 10 minus 1 is 9. U squared is 9. U is 3. This is the integral from 1 to 3. These u's cancel 1/2. U squared plus 1 du. This we know how to integrate. The integral of u squared is a third u cubed, and the integral of 1 is u. So it's this evaluated from 1 to 3. So that's 1/2. When u is 3, this is 27 over 3 is 9 plus 3. Minus when u is 1, this is a third plus 1. So this is 12 minus 1 is 11, minus a third is 10, and 2/3, which is 32 over 3 times a half, and we get an answer of 16 over 3. So if you haven't looked at the lecture already and you're seeing this for the first time, this is rather complicated. There's no way around that. And it takes some time to become familiar with the art of doing these kinds of integrals. So let me do a few problems, and if there are no questions, then we'll stop. These are really just like extended office hours for you to ask questions, and don't seem to be questions. So this is number 29 in the homework. The integral of 1 plus 1 over t cubed times 1 over t squared dt. And again, the natural thing is to say, well, what looks like the derivative of something? And the derivative of 1 over t is minus 1 over t squared. So if we let u, or g of t, be equal to 1 plus 1 over t, then du dt is minus 1 over t squared. So minus du is 1 over t squared dt. So if we make that substitution, this becomes the integral of 1 plus 1 over t cubed is u cubed, and 1 over t squared dt is minus du. That's what we get. That's minus a fourth u cubed plus a constant, which is minus a fourth 1 plus 1 over t, sorry, minus 1/4 to the fourth, minus 1 over t to the fourth. And that's the answer. Now, you can't do integrals if you don't have a good knowledge of your derivatives. So for example, for number 63, we have a trigonometric integral, which looks very complicated. The integral of tangent to the fourth secant squared x dx. And what you have to remember is that the derivative of the tangent is secant squared. So if I make the substitution u equal to tangent of x, this is the integral of tangent to the fourth, that's u to the fourth, and secant squared x dx, du dx, is secant squared x. So du is secant squared x dx. This is just u to the fourth du. That's a fifth u to the fifth plus a constant. That's a fifth tangent x to the fifth power plus a constant. Let's look at one or two problems that involve definite integrals. This is number 99. We have the integral from -1 to +1 of x times x squared plus 1 cubed dx. And if we let u be my function g of x that we're substituting equal x squared plus 1 du dx, or g prime of x, is 2x. So du is 2x dx. This is the integral from -1 to 1, x squared plus 1 cubed. Put the x over here, x dx. If I want to have a 2, I can multiply in by 2 if I divide by 2. So this is 1/2 the integral of u cubed du. And when x is -1, u is 2. And when x is +1, u is 2. And when you integrate from 2 to 2, that's always 0. This is 99. Let's look at number 101. The integral of 2x squared times the square root of x cubed plus 1 dx from 1 to 2. So if we let u be the function g of x, which is x cubed plus 1, du dx is 3x squared. And unfortunately, I don't have 3x squared, I have 2x squared. But of course, 2 is the same as 2/3 times 3. So 2x squared is 2/3 times 3x squared. So I can write this as the integral from 1 to 2, square root of x cubed plus 1 dx, times 3x squared times 2/3, which I can take outside, dx. So this is 2/3 the integral of the square root of u to the 1/2, 3x squared dx is du. And when x is 1, u is 2. And when x is 2, u is 8 plus 1 is 9. And the integral of u to the 1/2 is 2/3 u to the 3/2, evaluated from 2 to 9. So that's 4/9. 9 to the 3/2, 9 to the 1/2 is 3. This is 27 minus 2 to the 3/2. Any questions about any of these? This is basically the last topic in the syllabus. On Monday, we'll go over the review exam that is on Blackboard. Actually, I could divide 9 into 27, goes 3 times. So this is 12 minus, and this is 2 root 2. So 8 root 2 over 9 is a nice form of the answer. Any questions about this? I mean, my job's to answer problems in these sessions. Any problem anyone would like me to go over from this or previous homeworks? So I remind you that we've covered the whole syllabus now. And the review sheet for the final is just the sample exam, which is posted on Blackboard. And the actual final exam always follows very closely the structure of the sample exam. You'll notice that there are no extra points on the final. It's 100 points, and you just have to do it as much as you can. And I have office hours tonight, tomorrow, Friday, next Monday, Tuesday morning before the exam. So there's plenty of time to ask questions if they come up. If not, then I guess we are finished for the morning. Right? Okay, all. Be well. The last official one of these problem sessions is Monday at 11 o'clock. And I guess the final exam is on Wednesday of next week. Let me just double check. Yep. Wednesday, December 15th, 11 to 1 is our final. Okay, everyone. See you next week. Bye all.